Hi there, you're welcome back to my channel. So in this video, I'll be taking you through double integrals over general region. In our previous lessons in multivariate calculus, we've gone through partial derivatives, Lagrange multipliers, and so many other things. So if this is the first time you're on this channel, kindly subscribe and visit those videos to follow up the course. So let's see what you have here. So in elementary calculus, we only know of a single integral, right? So you have integral of a function of a single variable, right, with respect to that function. So that is a single integral, right, or integral over what? A particular single variable function. First of all, what's the concept of integral? What do you mean by integral? So if I have a plane, right, and I have a function of a single variable looking like a curve, right? If I want to find the integral of this over a region, because it's a single variable, I always take it over a single region, right? So if I have my y-axis and I have my x-axis here, and I want to integrate this single variable function over x from a to b, what I'm trying to do is I'm trying to find the area of what this particular function from a to b. So I simply what um divide my a. Okay, so apparently if you remember trapezium rule, the midpoint rule, the Simpsons rule, to find an integral, like we are summing the area of what this particular function over this range. Okay, we are summing the area of this particular function over this range. So that is the concept of what the integral when you are dealing with a single variable. But remember that you're having a multivariable, right? If you're having a multivariable, then it means that you are going to have. So you saw that initially we had a single line, right? A single line we are trying to um, integrate over, right? But in a multivariable dimension, we always have what you call a plane. So if you're having yx, right, you have something like, let's say, a shape like this. You have this, right? So you have two functions. You have two functions here. Let's say you have two functions here. So over these two functions, you let me draw it something like this. So you have a plane, okay? So this is a plane. So if you have a function of xy, remember that this function takes in two inputs. And if a function takes in two inputs, then it's going to take the form of what? A plane. Because it will have a two-dimension. So this is 2D, right? So for 2D, you're going to have something looking like an area, okay? An area. And know that an area can fully be defined by what? Its two sides. So we cannot only integrate over what? X, right? Like as we did in a single variable. So let me clearly show you to you here. If I have something like this, right? Then this is my x-axis and this is my y. Initially, when this was a single variable here, without this, remember it was a single what? A variable. So it looked like what? A curve, right? So when you got this was a single variable. So if you want to find the integral over the region AB, it's simply what? Finding this sum of all the what? Pieces of this function over this interval. But in this case, we want to fully find the area. And since it's a two-dimensional shape, it has two dimensions. It has this dimension and it has this dimension, right? You say that length times breadth, or you say that the width times the height, or something like that, right? So for that reason, this shape here can fully be integrated over using both the x axis and y axis. Here I use only a and b, yes, because it's just a single dimension, right? Just a single dimension, right? So this one is a full plane, right? It's a full plane. So I cannot just take a and b for the x and expect to integrate this. No. I still need what? The component of what? The y, right? So always, if you are integrating over general region, that is double integral over a general region, we have two forms. We always have two forms. So let's see. The first form is a case where you have, so as I said, here's okay, here's y, here's x, okay. So here we are having two curves pointing in the parallel to the x-axis, okay. So here our curves are parallel to the x-axis, and these curves are meeting somewhere here, okay. So this is a true curve. So I have, let's say, this first curve to be y is equal to j1 of x, right? Then this is also equal to y is equal to j2 of x. They are two separate curves, right? And they've converged here at this point, obviously. So here they are all moving to this way. So you realize that these two separate curves have created a two-dimensional shape, like an area, right? It's like a park, right? So whenever you have something like an area here, and we want to integrate over this region, you cannot only differentiate over what its boundaries on the x. So there's a eight boundaries on the x, let's say a, and eight boundary on the x axis, this side is b, right? You realize that it is also having boundaries on the y-axis because it's a two-dimensional shape. So this is where you are going to take integral over x, integral over y. That is what we call double integral. So it's generally represented with two integral signs. Then you bring your f of xy, integrating over x and y because it's an area, right? Integrating over x and y, it's an area, right? So this is our area which we want to integrate over. Then the a. So this the a is showing that we are differentiating over an area. Okay, we are differentiating over an area, not just a point, as we do in the single variable the x dy, right? That is when only a single variable is changing. But in this case, a two variable is changing, so it's being integrated over a big area. So you say the a, and remember that for every integral, it is done over a region, okay? And the region here we represent it with d, okay? So always, whenever a problem is given, d is defined in the question. Sometimes you have to deduce the region over which you are going to integrate, okay. So that's one thing you should take note of. You have to deduce, know your d. So in this scenario, this is where our plane is having two curves parallel to x. So once it's parallel to x, you realize that the limit point for the x size is a and b, right? So for our case one, our double integral right now, and always take note, we always make constant limits move to the outer integral, okay. So here integral ab, so always, because ab is what a constant, we move them out, okay. The purpose of definite integral is to arrive at a constant, so we always push the constant integral to the outer integral, okay. Then we push our inner, which is a y. Realize that the y is having, so this is our first y and this is our second y. So we have g1 of x, we have g2 of what x. So let me do it this way. I don't know their magnitude, so let me obviously write it according to, so you know that when you are moving higher upwards the y-axis, it increases, right? So it's assumed that g here should be g1 of x, here should be g2 of x. So to write the limit for the y side, it should be g1 of x, here should be g2 of x. Then your function of x y will come, then the a, that is all. And your, now your area is simply what we also have for something we call order, okay. So which one are we differentiating first? Remember that the y side here is the one which is having what the functions, and the ones which are having the constant limits are outside, and that is for the x plane. So here we are differentiating the y dx. Take note, we are differentiating what the y dx. So our first case for our double integral is showing us clearly the regions over which we are what different integrating, and as well as how we are the order, okay, as well as the order which we are integrating, okay. So this dy dx, because I said always put the constant limit at the outer end, always put the constant limit at the outer end. So knowing the first case, let's see the second case. So for case 2, right? So for our second case, I'll have my plane, here's x, here xy, right? So now I'm going to have two functions which are parallel, right? Which are parallel to the y-axis. So this time around, I'll have one function this way, and I'll have another function this way, right? So this function here will, let's say x is equal to h, do it well. So I'll have x is equal to h1 of what? X, right? Sorry, since it's s equals to h1 of y, and you know that as for x-axis, the more you move to the right side, the more it increases. Is that not it? So you're gonna have x is also equal to h2 of what? Y for this side. So here's the area upon which we are integrating. It's a two dimension, the x side and the what? Y side. So the y side will be here and this way. Okay. So here we have A and B. So we can see the two scenarios. So from our first scenario, we realize that we had our function, our curves, which is parallel to x. Here the curves are parallel to y. Okay. So to find our double integral over region d f of x y dA, this will equal to integral. And ask yourself, for this second case, which of our axis is having the constant limit? That is the y. So meaning the y will come out as AB, right? And our x will come out as what? H1 of x, H1 of y, H2 of y, and f of xy. Then we will now see that we have to differentiate x, so we have to integrate over x before we move to the outer constant limit, which are on the y. So we say dx dy, right? Because we are doing that of x within. This is the inner integral. We are doing it with respect to x because that possesses the function. And the one with the constant is moving out because that is a y. It's having the constant limit. The goal is to arrive at what? A constant figure, which is a definite integral. So this is the concept of what? Double integral. The concept of double integrals, where you are integrating over a region which is two-dimensional space, and hence you cannot fully integrate over a single what dimension. You have to go into all the two dimensions, both the x and the what and the y. So let's take a couple of properties of double integrals. Then after we take some examples in this section. So let's see some of the properties of double integrals. Properties double integrals. So for the properties of double integrals, I'll have, it's almost the same as that of the single variable. So if you have an integral of a function f of xy over the region D plus another function f of gxy all over all dA, right? Then we can decompose this into integral d of what? F of xy dA plus double integral over region D of g of xy dA, right? So this is a normal property, is a normal property. As well as if you have a constant, right? If you have a constant multiplying the function of xy dA, you can just put the constant out and you introduce a double integral over the same region f of xy dA, right? Yeah. So this part is a special property. So now it says that if the region, right, the region over which you are integrating over, the region D, if the region D can be split into two separate regions, such as D1 and D2, then the integral can be written as double integral over the region d f of xy dA is equal to double integral over the first, region, because now you are trying to say that if the region over which you are integrating over can't be decomposed or can be separated into two separate regions, then we can decompose our integral over these two regions, right? So that you can get something like f of xy, right? Over to 1 plus double integral d2 f of what? Xy, right? So these are the few properties, and now let's see how to solve some couple of examples, right? So let's take our first example. So we have to evaluate the following double integrals. So integral over the region D e to the power x or y dA, okay, where d is equal to xy, then 1 is less than or equal to y, less than or equal to 2, y less than x, less than or equal to y. So looking at this question, we have a function e to the power x over y. This is an integrable function taking two inputs x, y. Okay, and we are going to say that the original language of the integrate is what? 1 less than or equal to x, y less than or equal to and x less than or equal to y. These are the intermediate of which we are going to integrate. So we can either graphically represent our region or show that we can access our function and so take note. In our subsequent tutorials, we do change of what limits. We have cases where you can't directly integrate where your x is in the function, so you have to switch. But for now, let's go by the normal way as it's the first step in this particular section of the course. So for here, as I told you when we started, I said that always make sure that your constant limits are always the outer boundaries. So we start. We know that for the y side, the boundaries are 1 and 2. So we can write 1 here and 2 here, right? 1 here and 2 here. Then your inner, your x has a boundary y and y cube. You know y is the lower limit and y cube the upper limit. So you write what? Y and then write your y cube here. Then our function e to the power x over y becomes here. Then our function dA, the area becomes what are we differentiating first? The x raised to become to the x dy, x dy. So we have got a nice representation of what our double integral here. What we need to do is to apply our calculus knowledge or the previous knowledge you have in elementary calculus and justice to this. So we always integrate the inner integral first before we come to the outer. So if you have 4, 5, 6 integrals, and it's always make sure you put the inner one first, the one attached to the function before you put out. Okay. So now I'm going to put the inner one. Then the inner one I'm differentiating with respect to x. So let's see how we do that. So integral 1 to the integral. So if you have e to the power x over y, you are trying to say the x face. We are integrating this with respect to x. How do you integrate this with respect to x? Here we apply partial derivatives here, but it's integral. So in the presence of x, we consider y to be a constant. Okay, y becomes a constant in this graph. We don't treat y as a variable because we are only integrating with respect to x. So if y is a variable and if you want to integrate with respect to x, we know that for exponential functions, integral of exponential function, you have to differentiate with the numerator, that the power. Then after you divide the whole expression by power. When I differentiate the power here, it's like e to the power of u, where u is equal to x over y. So you differentiate u, you get the u over the x, right? Then you simply divide it by what? You simply make our doing a subject. But we don't want to go through that process. That's why simply the general statement is that you always differentiate the power and divide the expression by the differential. So now let me differentiate the power with respect to x. What am I getting? I'm getting 1 over y. So I'll divide the whole expression by 1 over y. So I'm going to have the outer integral is untouched because we're not doing the flower box. The brackets here, I'll have 1 over 1 over y multiplying e to the power x of y. Then I'll apply my one upon y over cube here, and I'll bring that to y because I'm done with x. Nice. So systematically. So at this point, we're gonna have 1 to here, but we know that 1 over 1 over y becomes what? Y e to the power x of y. Then have y cube to y. So we still want to simplify this again now. I'll have integral 1 to 2. When I put y cube here, what am I getting? So let me simplify. I'll have y multiplying e to the power. So wherever I see x, I'll put y cube here. Y cube y minus y multiplied to the power. Here I'll put y there. Y of y minus minus I repeated again. We'll have a y to y. Still looking out for multiplication 1. We know that here becomes y squared, right? I'm gonna have y e to the power y squared minus here y over y is 1. So I'm having y e that's 1 to 1. So now I'm done with my what inner integration. I'm left with the outer integration. For the outer integration, I'm only integrating my function here with respect to y. With respect to what? Y. So how do I integrate this with respect to y? So let's see. So I simply have so with this one, since I'm integrating with respect to y, every y is a y, right? Every y is a y. So how do we do that? So you know that for this part, you simply have to differentiate the numerator, and that will be given as what 2y. 2y, then you simply divide it by this. So here we decompose using the property above. So 1 to y e to the power y squared to y minus 1 to y e to y, so that we do it separately. So at this point, we simply having this power, you have to just differentiate the numerator, then divide it by the expression. Okay, just that is also like the chain of variables, but that is what it has been catered for in what integral. So this is double integral, it's a step up. So here we are interested in the concept, okay, not the manipulation of derivative and integrals. So whenever you have your power here of the numerator of the when you have the power of the power, haha, yes, if you have that greater than the coefficient of your function, which is also the function, then it means that we can what differentiate the top one and divide to cancel, right? When I divide the top one, I'm getting what 2y, is that not it? So I'm going to have y e to the power y squared over 2y, right? As we integrate, then you bring 1 2, take notes, that is what we do, minus here is a simple thing here, e is a constant, remember. So since e is a constant, you have y here. When you integrate y, you are simply going to have y squared on 2, okay, multiplying e 1 2, that's all. Here my y is cancel y, so it looks like I have a y to the power squared on 2, integral from 1 to 2. Here to I'm having y squared on 2 e from 1 to 2. So I simply make my substitution. Wherever I see y, I'm going to put what my upper and lower limits, right? So here I'll have e to the power. When I put 2 there, I'm getting what 4 over 2, right? Minus when I put 1 there, I'm having e to the power 1 over 2. I'll write 1. That is for the first part. Minus when I come to this side, wherever I see 1, when I put 2 there, I get what 4 2 multiplying e, right? Minus when I put 1 there, I'm getting 1 multiplying e. So here, if you have this expression, e to the power 4 or 2 minus e to the power. So let me maintain this here and go on to my simplification. So let me maintain e to the power 4 because it's on the power 4. Now minus e to the power 1 over 2. But here, see, I have Here we got TD, okay, 4 over 2 TD. So TD minus half A will be 3 over 2A, right? So minus 3 on 2A, because I'm getting 2 minus half, that will be 1.5. Okay, so E over 2 minus 3 over 2, negative 4 over 2, I get negative 2, right? So my final answer becomes e to the power 4 over 2 minus 2a to the power 1 or 2a. Okay, so thank you for being with me in this video. This was quite a long tutorial. So don't forget to subscribe, like, and share. And I'll be posting a lot of tutorial videos on double integrals over general algebra. So see you here.